This video is about fluid dynamics and how to express your concepts through writing when solving problems. So let's start by looking at a problem. So here's actually the solution to a problem. I've got a pipe that changes diameter. And so when that happens, I'm kind of thinking in my head, I'm thinking, oh, it's a continuity equation. So maybe I write that down as my strategy. Well, that's not quite enough. Because really, I want to know a little bit more about where the continuity equation came from and what it means. So a better description would be the pipe's diameter and area are inversely proportional to each other. So that's great because I'm using the idea of proportionality and using that phrasing. So they're inversely proportional. One goes up, the other goes down. In fact, the next sentence, that's what it says. As the area in the pipe narrows, the speed will pick up. But that really doesn't describe where that came from. What concept or what principle am I using? And I'm using this. I know it's a continuity equation. It's all about flow rate, but let's talk about where the flow rate comes from. So the flow rate must be maintained to conserve the flow of mass. It's a conservation of mass problem. And then it says the pipe's diameter and area are inversely proportional to each other. As the area in the pipe narrows, the speed will pick up. That's a great explanation because I'm talking about where my concepts are coming from and how it's applied, and I'm using the right vocabulary by inserting the word proportional in there where it's appropriate. Let's look at another one. This one's going to be a little bit more to it. It's going to have multi-steps to it. So here's the problem. There's a lot to do in this problem. I looked at my givens. I can see I've got the continuity equation in black, and I've got Bernoulli's equation in blue. At the very bottom, I can see I'm doing something with the gauge pressure. So this might be the strategy that you would think of. Well, if I'm solving this, I'll start at the end of the problem, gauge pressure. So my strategy is gauge pressure, then Bernoulli, and then I'll go with continuity equation. Again, not enough shown. So now you're thinking, well, wait, that's kind of in a backwards order. I'll be real clever. I'll reverse the order. So this is really the order that's on the page. I start with the continuity equation, then Bernoulli, then the gauge pressure. Well, nice. It's nice that you have the order because it does flow better, but still you need to add more. So let's take another look at the strategy. And let's talk about where these things come from. So the first thing I'm thinking of when I'm getting the problem is gauge pressure. So let's talk about where the gauge pressure is. So it's a difference in pressure. So that's telling me, someone else, a user, that you know what the gauge pressure is. And then Bernoulli. Well, Bernoulli is a conservation of energy thing. So let's talk about that. The difference in pressure can be found from the energy lost in changing speed because the energy per unit volume is conserved. So great. I didn't use the term Bernoulli, but I used the concepts that Bernoulli is expressing. Now let's keep going with the top. The flow rate must be maintained to conserve the flow of the mass in the fluid, and the area is inversely proportional. Therefore, the velocity changes when the water enters a different diameter pipe. So that's great. It's telling me continuity equation, but it's not saying the words continuity. It's actually telling me that the flow rate must be maintained to conserve mass, and that because of that, the velocity and area are inversely proportional. So again, I'm using the proper vocabulary, and then describing exactly what my expectation is, by the velocity changing with a different area. But it's in a backwards order. This is how I think about it, but when I'm writing it down, I should start from the beginning, go to the middle, and then go to the end. So I just reverse the order like that. Now let's try one simple problem that you can do from scratch. So here's the problem. If the pressure in your head was not allowed to equalize, then your eardrum, with an area of 7 times 10 to the minus 5 meters, would rupture if 7 newtons was applied to it. How deep below the surface would you need to travel for the eardrum to rupture? So I'll start with a little picture. Now what I'm going to do is I'm going to actually pause the video right here, or you can pause the video right here. And when you pause, write your own strategy about what will happen. And let's compare yours with the kind of strategy I'm looking for. So pause the video right here, and I'll let the screen count down. So here's one of the strategies that you may have come up with. The strategy is P equals P naught plus rho GH, F equals P gauge pressure times the area, which is correct, except it's not well written. It's too much math formulas. So let's take a look at what it looks like and then talk about how we'd write it out. So here's what it all looks like. In black, I've got the givens, and kind of that purplish color, I've got the equation for pressure, and then I have the gauge pressure is from the depth pressure, which is the hydrostatic pressure. And it looks like the third line is really key to this. The gauge pressure is equal to rho GH. And then from there I plugged in my numbers and units and solved. Great, but now I got to write it out. So my strategy is the pressure at the bottom is due to the sum of all the pressures above. So I'm defining what the gauge pressure is that I'm going to be using in the blue text on the screen. 7 newtons is the gauge pressure, so I went ahead because that can be a little tricky. Some people may not realize that's the gauge pressure. And since P minus P naught is the gauge pressure, rho G8 is the gauge pressure responsible for bursting the eardrum. Okay, just describing where it's coming from. And I'm going to find the gauge pressure to burst the eardrum and set it equal to rho GH. So in the blue text, the third line down, it is exactly that statement. P minus P naught is equal to rho GH. That's just math version versus the gauge pressure to burst the eardrum and set it up equal to rho GH. So I'll give you an idea of how to write your strategies in words and not just equations.